This is Lesson 1 of Unit 4, Applications of the Derivative, and Lesson 1 is on interpreting the derivative verbally. So we're going to finish out this lesson by looking at 3 examples where we're going to use clues from the units to recognize how to interpret the derivative as they relate to the scenario given. Okay, the first one. Example 4. Suppose you launch a water balloon from a giant slingshot. Let S of t give the distance in feet that the water balloon traveled from its initial starting point as a function of time t in seconds. Explain the meaning of the derivative notation. So what we want to notice here is that we have ds dt, so that is going to be the distance, the rate of distance over time, and we have a t equals 2 right here. So that is, want to look at the units, t is in seconds, so this is at this is at 2 seconds. So we're looking for the rate at 2 seconds. And so we can also call that s prime of 2. And we're getting 38 feet per second. So we would want to say when t equals 2 seconds, the water balloon is moving at a velocity of 38 feet per second. Okay, example 5. The total cost in dollars per person of an airplane flight with n passengers can be calculated by Derivative Airlines using the function c equals f of n. What does it mean to say f prime of 182 equals 58? Now, you want to go back and see that our n represents passengers. So we have 182 passengers, and we have a rate of 58 passengers, or $58 per passenger. So that's why it's important to think of c prime of 182 as dc dp, or dn, for number of passengers. So it's cost per passenger. So we can say that when 182 passengers are on a flight, the cost per person, I guess you should put passenger, for the flight is $58. Okay, example 6. Non-potable water, in case you don't know what that means water that you can't drink. It's not exactly contaminated, but it's not up to drinking quality water. Non-potable water is being pumped into a processing center where the depth in feet of the water at time t in hours is given as y equals h of t. Interpret the following statements using proper units. Okay, so this is just interpreting the function's value. So t is in hours, so that's 7 hours, and 5 is the depth. So we can write after 7 hours, the depth of the tank so the depth of the water at the processing center is 5 feet deep. Okay, for part B then, we have the derivative at 7. So now we're talking about the rate of the change of the depth of the water. And so at 7 hours, the depth of the water is, I can say increasing because the 0.6 is a positive number, at a rate of 0.6 feet per hour. Okay, next we have the inverse. So now you want to remember we're reading this backwards. The 9 is going to represent the time, and the 7 is going to represent the depth. So writing this backwards, we would say when the depth of the water is 7 feet, the water has been pumped into the processing center for 9 hours. And then finally, the last part, now we have the derivative of the inverse. So we're going to look at the rate in a backwards way. So we want to see that it's going to be time per foot, so to speak. So that's how we're going to do that. So again, since it's backwards, the 1.4 is going to represent the time, and the 7 is going to represent the depth. So we're going to say when the depth of the water is 7 feet, it takes 1.4 hours for the depth to increase, because it's positive, 1 more foot. So it's looking at the rate upside down. Okay, so in lesson 2, we are going to continue to look at rates again, but this time we're going to look at our straight line motion rates, and we're going to do the same kind of ideas, interpreting the derivatives and understanding their meaning. So I hope you enjoyed this video. Again, if you have any questions, please feel free to ask in class.